Good afternoon. Welcome to lecture 11. This is going to be on diodes. And so we started this topic a little bit in the last lecture. Just some announcements before we start. So homework number 4, that's online. That's due by way of Gradescope this coming Friday. So lab number 2 continues this week. The pre-lab is due at the beginning of lab this time, or I guess by Gradescope as well. Lab number 3 is going to be next week, and so the materials for lab number 3 are already online. I should say that Ali, one of your TAs, is going to be out of commission this week. Hopefully he'll be back next week, and so some of the other TAs will fill in. So if you're in the Tuesday lab section, he won't be there, but maybe Kieran will be there instead. Who's in the Tuesday lab section, by the way? Okay, yes, I know. Okay. Any change in whether you talked to Kieran? Okay. Was there a... Anyway, I'll talk to you later. Or I'll talk to him to figure out what's going on. Any other logistics we should talk about? Looks like no. So lecture topics will be doping, which we started last time, and then semiconductor currents. And then we'll see how far we get into diode operation. We might not get too far into that. But last time we started looking into currents in semiconductors. And I think just to start off, I just have this little picture here that I drew in a previous lecture. This is what an actual diode's IV characteristic looks like. And so you know that it turns on at a certain voltage VDO, but it doesn't turn on immediately at this certain voltage. And I guess I even drew this a little bit incorrectly here. Because it really should be going through 0 at 0 volts. And so let me fix this just a little bit here. Yeah, I'll destroy the whole thing to fix it, but we'll go ahead and do that. So if that's this going there, then this should be going through 0 there. Then it starts climbing up, and it basically asymptotes to that VDO there. Okay? But this is the equation for the diode response. So that's the I. The current going through that is some saturation current times the exponential of V over N times V sub T. All of these things will be defined in due time here, but this is what we're trying to get at. We're trying to get at understanding why a diode does this. And that'll happen in actually the next few lectures, because there's a good amount of physics to go through to understand that. And so this is where we were last time. We talked about semiconductors, we talked about insulators, we talked about conductors, and really a semiconductor is just like an insulator if you don't do anything special to it. And so if I had silicon atoms, which we talked about last time as them having atomic number, well, we can bring up our periodic table here. So this was last time as well, but in our periodic table you see silicon with atomic number 14. And what that means is that the first 2 orbitals are filled, right? The first orbital takes 2 electrons, the second one takes 10. Sorry, it takes 8, so that's 10 total. And so there's 4 left. And those 4 left, all you need is 4 more in order to make a perfect 8 in the outer shell of silicon. And so the way that it does it is the same way that, say, another insulator will do it, like say carbon, for example. What it does is it joins together with 4 other silicon. I guess I don't have that picture here, but picture this silicon atom joining together with 4 other silicon atoms around it, and then its orbital gets filled with 8 electrodes, as I'm showing right here by the black dots. Okay, what this picture is showing is what happens when we dope the silicon. And so when we dope the silicon, what we're doing is we're really replacing silicon atoms with another type of atom. And we can make the silicon do special things if we choose an atom that has either 5 valence electrons, that's phosphorus or arsenic, or we choose something with fewer than 4 valence electrons, that would be acceptors like boron, which I'm about to talk about a little later on. But if we go ahead and replace the silicon with a phosphorus, which is what we did last time, what happens is 4 of the phosphorus electrons go into place in that valence shell to give phosphorus and the silicons around it, all 8 valence electrons were their happiest. And happiest means that's their lowest energy state. Okay, so then their lowest energy state when their valence band is filled, but now phosphorus has got a 5th electron. And so that electron can't go anywhere. It's not going to be happy in the valence shell of phosphorus because that valence shell is already full. So what that electron is going to do is just move around between the different atoms. Okay, so this electron suddenly becomes very free. That's exactly what happened in a metal. So a metal was basically a cloud of electrons. In a metal, you had all the atoms with a single electron in their valence shells. And that single electron is very unhappy there. So when you put all those atoms together, the single electrons from all the metal atoms just go out and form a cloud of electrons that you can control now using voltages. And that's how current flows. It's through those electrons in a metal. In a semiconductor, though, you don't have that naturally, but you can get that by just replacing silicon with a phosphorus. So you notice we've replaced silicon with phosphorus. There's that electron there. It's free to move around. And if I put an electric field around this, that electron will follow the direction of that electric field. Okay? It'll go the opposite direction of the electric field. Okay, so we covered that last time. And so this kind of summarizes a lot of this here. So I've got 1s and 2s and 3s and stuff that sort of show where each of these different things is talking about in the diagram to the right. We went through that last time. But what I want to end up with is you can see that every time I substitute a silicon with a phosphorus, I'm adding another electron. Okay, so every time I do this, this is becoming more metal-like. In a metal, every single atom contributes an electron. In this case, you know I can't have every single atom contribute the electron because otherwise it would no longer be silicon. Right, so it's got to stay silicon. I can only substitute with a certain number of atoms here. But if I get that concentration of phosphorus very high, I'll have a lot of electrons. And maybe I'm not going to get 1 ohm of resistance across a certain amount, but maybe I can get something like 100 ohms across that. That's still a lot smaller than infinity, which is what you have with an insulator. Okay? And so this is a very important thing that we're able to do with semiconductors. This is part of the reason why semiconductors are able to create the diodes and transistors that we're about to talk about. It's just this ability to create a metal-like substance out of something that was originally an insulator, and that's happening just because we're doping that silicon. We're replacing silicons with phosphorus. So the question is, how do you replace silicons with phosphorus? Well, that goes into a class that, that goes into material that this won't cover. That will be in ee143. Maybe ee130 talks about that as well, but 143 is where you actually get to do it in the lab. And you'll see that it takes high temperature processes or some kind of high energy process to just throw that phosphorus into the silicon. So right, you can just bombard the silicon with phosphorus. If it's high enough energy, phosphorus gets in the silicon. You then heat it to repair damage, but you end up with phosphorus in the silicon and a lot of electrons to move around, and you've created something just like a conductor. Okay? And so with what I just said, the larger the concentration of donors, which we call capital N sub D. So capital N sub D is the concentration of donors. The greater the number of electrons available to generate the electron cloud, which can then be controlled by an electric field, and so the better the conductor. And so more nomenclature for you. Little n, why we use little n, I'm not sure. But little n is commonly the number of free electrons in a donor-doped silicon. And so because we use n for that number of free electrons, we call this n-type silicon. Okay? Yeah. What's the reasoning for that? Okay? If you're a CS person, what's the reason for NP complete? Why are they still also using N and P? I don't know. But we're going to use P for acceptors very soon. So N and P somehow are significant letters in electrical engineering and computer science. Okay, so let's talk about acceptors. What's that?
It says that actually P stands for positive because
yeah, okay, that's one. No, so he's saying N stands for negative, P stands for positive. Yeah, I suppose, but I don't know that there's really that history there, but that does make sense, doesn't it? It does make sense to me. So N is the number of free electrons. So acceptors now. Let's talk about acceptors. So in this case, we stuck this with phosphorus. Okay, but an acceptor is an element with 3 valence electrons. Not 4, not 5, but only 3. And so that's boron. And so if we go ahead and do the same thing, you can look down here. I'm now substituting for silicon a boron atom. And so that boron atom, it actually will give me 3 electrons. So there's 1, there's 2, there's 3. 3 nice electrons in there. This thing's too thick. But you can see I'm missing an electron right there. Okay, what is a missing electron? We call that a hole. Okay, so there it is. So I have a hole right there, and that is a missing electron. So I guess, let me equate these to statements that I make on the next page. So 3 electrons from boron are not enough to complete the valence shell. So that's number 1. There's my boron there. Okay, and so it leaves a hole. And so there's my hole. Call that an H plus for hole. And that's 2, I guess. So it's left a hole. And that hole can move because an electron can move into it. So the only way a hole really moves is an electron moves into the hole. Okay, so we talk about the holes moving, but really the holes don't move. Electrons move into them. And when an electron vacates one spot to go into that hole, it creates another hole where it used to be. Okay, and so in that way you can think of the hole as moving. So let me go green here and say that if this electron here decided to move into that hole, oops, that's too thick. So that electron decides to move into that hole, so is there, then it creates a hole in itself there. And in that way it looks like the hole has moved. And so holes propagate. Electron can move in this hole. I guess that was 3 here. I guess I have to do this. And so holes propagate. So basically my hole motion was in that direction from this point to that. And it can keep going all the way through, provided there's an electric field to make that happen. Right? Why would the electron want to move this way? An electric field will make it move that way. Okay? Let me finish my picture back here too, just to be complete. That was okay, so it's a very similar thing to what happened when we put donors in here, except now we have a larger concentration of acceptors. So the larger the concentration of acceptors, like boron we have in here, the greater the number of holes available for current flow, and thus the better the conductor. And so now P, like I said, represents the number of free holes. And the number of free holes is then about equal to the concentration of acceptors, which is N sub A. Okay, so if I give you a concentration like N sub D or N sub A, N sub D is the concentration of donors, N sub A is the concentration of acceptors, that tells you there's that many, for the case of donors, electrons per cubic centimeter in that material now. Okay, and same thing for holes. There's that many holes per cubic centimeter if I've doped it p-type with doping concentration capital N sub A. Okay? And so in this way we're converting a semiconductor to a conductor by doping with donors, okay, which either generate an electron cloud if it's with donors, or with acceptors generates a hole cloud. All right, so just a couple things that I could say about electrons and holes and how many there are in silicon. So remember we talked about silicon and the fact that I can heat it up and I'll create an electron in a hole. I guess maybe not everyone remembers that. That may be important enough for me to go back a bit here. How many of you watched the video lecture who weren't here on Friday? Did everyone do that? I see smiles, which means no. Try to keep up with those video lectures, because if you don't, you're going to get behind and it's going to be trouble. And if I think there's trouble, what I'll do is I'll look at my YouTube videos, I'll see how many people have watched them. If not enough, I'm going to stop posting them for a few days. Right? I'll always post them, but I'll just delay it, right? I claimed that I would delay it the first day. I haven't been doing that. But if you're falling behind, I'm going to delay it to force you. Well, that may make you fall behind even more, but I need to do something to force you to watch those videos, okay? Let's see, this is lecture 10 right here. So in lecture 10, yeah, let me go ahead and bring that up. So we talked about, it's right here. So see, we talked about the fact that you always have electrons and holes even in undoped silicon. Okay, and the reason why that happens is because there's enough energy with the fact that this is at room temperature, right? So there's no energy when you're at 0 Kelvin. At 0 Kelvin, nothing's moving. But as soon as you put a little energy in there, that temperature goes up. And this is all the way up at room temperature, 273 Kelvin above 0 Kelvin. Right? So there's enough energy in this system that there are some electrons that can leave this covalent bond here. And once they leave that covalent bond, they create a hole. And so in that case, you always have some holes and some electrons, even in intrinsic silicon. Intrinsic means undoped silicon at room temperature. Okay? So you always have some electrons and holes. And so there it is. Every time an electron moves out, if I create an electron, I also create a hole. So that in intrinsic silicon is necessary because it keeps everything neutral. Right? So the electron and hole will still cancel each other out. But I still have electrons and holes. And so N sub I is the nomenclature used for the concentration of free electrons in intrinsic or undoped silicon. And N sub I at room temperature is equal to 1.45 times 10 to the 10th per cubic centimeter. So that means the number of holes or electrons per cubic centimeter is 1.45 times 10 to the 10th. Okay, that seems like a lot, but how many atoms are in silicon in a cubic centimeter? 10 to the 23rd, right? So there's a lot more atoms in the cubic centimeter than silicon. So in intrinsic silicon, the P concentration or the hole concentration equals the N concentration or the electron concentration, which equals N sub I, which equals this 1.45 times 10 to the 10th. Okay? And so as a rule of thumb, at any given location at equilibrium, the product Pn equals N sub I squared. Okay? Now that's obvious for intrinsic silicon, but the interesting thing is that if I dope a region, okay, with N-type or P-type, I'm going to increase the number of electrons there if it was N-type, but automatically I've decreased the number of holes there, okay, because that product Pn stays the same. Okay, another way to write this here is, say I take silicon and I predominantly N-type dope it. So say I predominantly N-type dope the silicon. That means that N sub D, the N-type doping concentration, is much greater than N sub A in that particular portion of silicon. Okay, in that case, I could say that the N-type concentration, or that number N, the number of free electrons, is about equal to N sub D. Okay, it's pretty much equal to N sub D. And because of that, I could say that my hole concentration in that part of the silicon, that slab of silicon, is just going to be equal to this N sub I squared divided by N sub D. Okay, basically I'm saying my Pn product is constant. Okay, I could do the same thing. If I predominantly, say I predominantly dope P-type, which means that my N sub A concentration is much greater than my N sub D concentration, then I could say my P concentration is about equal to N sub A, and my N concentration is going to be N sub I squared divided by N sub A. Okay? So if I know my N concentration at any location, I know my P concentration too, is what that's basically saying. All right. So now, from here, with an understanding of how we're doping our silicon, so we're putting electrons and holes into them, I guess the last thing I should do to be complete is go back to our periodic table here. So I'm trying to bring up. And in this periodic table, I've already got phosphorus and arsenic here, and so these are donors. And then I can also bring out boron. I'm out of colors. Let's do that in blue. So boron here, this is our acceptor. And there are other acceptors too that you can use, but you'll see that predominantly people use boron there. Okay? So all the different materials we're using in CMOS, there's a lot more materials out there, but there's only a subset that are very interesting to us for diodes, CMOS, bipolar junction transistors that we'll soon talk about in great detail. All right, so let's now talk about current flow. We know how to change our silicon so that we actually have them conductive, and that's by doping. But now once we have them conductive, now currents can flow once we put electric fields across them. And so there are two possible types of current. Okay, one of them is called drift current, the other is called diffusion current. So I already have this prepared here for drift current because you already know what drift current is. This is the current that when you have a resistor, you put a voltage across it, electrons flow. Okay, and so I've also drawn a picture of that. So just to be complete, drift current is a current that flows upon application of an electric field across a material with free charge carriers. So it either has electrons or holes. A metal is such a material, right? A metal is going to have a lot of electrons. You put a voltage across that, the electrons will go against the electric field, which means they're flowing, and you've created a current with those electrons, okay? And so that's what this is showing. I'm showing a slab of material here. I put an electric field in this direction. If I put an electric field in that direction, if this material has electrons, they move in the opposite direction to the field. If it has holes, positive charge, then they move in the direction of the electric field. Okay? And anytime these are moving, I'm creating a current. And so I'm interested in the expression for this current. So this J here, instead of an I, I'm more interested in current density here. Okay, so basically I'm interested in the current that's going through that cross-sectional area. Okay, how many charge carriers per second are going across that cross-sectional area, right? And that gives me a current density. And so for electrons, let's determine this. Okay, so I can write J sub n for electrons, and this is going to be an equation for drift current, so I'll write drift there. That's going to be equal to the charge on an electron, which I'll call Q sub n. And so that's really the charge density. Charge density of electrons. And since that's a density, I'm going to make that charge per cubic centimeter. Okay, I'm going to take that charge density and then I'm going to multiply it by the velocity of the electrons. So that V is not voltage, but it's the velocity of the electrons. And that's going to be, as all velocities should be, in some kind of length per time, so centimeters per second in this case. Okay, and so I can write out expressions for this. So you should know from physics that there is a unit charge, right? Each electron has that unit charge. And that unit charge, I'm just going to call Q, which they also call in physics all the time. It's an electron, so it's negatively charged. So I'll put a minus sign in front of that. So that's Q times the concentration of electrons, which I just said is N. Okay, so this Q, again, that's the unit charge. And that's equal to 1.602. Let me give myself more space. 1.602 times 10 to the minus 19 coulombs. Okay, but that's a number that I think you all have seen before in your physics classes. And this then has to be multiplied by the velocity of the electron. So the velocity we normally write as minus mu n. It's minus because the electrons are moving the opposite direction. right? So my x-axis is this. There's the positive direction of x. So anything moving in the opposite direction is moving in a negative direction. So I'm saying minus mu n here times the electric field. So mu n times electric field, let me label that electric field. Mu n times electric field becomes my velocity. And so what is mu n? Mu n is equal to, by definition, what's called the mobility of electrons in silicon in this case. And so there are all sorts of mobilities. And so the mobility of electrons in silicon, at least at a certain temperature and for reasonable doping concentrations, and I'll tell you what reasonable means later on, is on the order of 500 square centimeters per volt second. Okay? And so what is mobility? Mobility here models the fact that electrons collide their way through a material. Okay, so let me write that down. So models the fact that electrons collide their way through a material. So, what does that look like? I mean, when an electron is moving through a material, basically, I have a lattice of atoms here. I don't know why that came up. Boy, everything wants to come up. So I have a lattice of atoms, so draw it like this. Right, so each of these are an atom with some of their orbitals and that sort of thing. So when an electron is moving through this semiconductor, so there's my electron, okay, it can't ballistically just go through all of this stuff. Okay? What the electron does, it can actually if you have very few atoms between it. So in some of the latest generation, I wouldn't even say latest generation, some of the future type of devices people are working on right now, they actually will get some ballistic motion of the electron where it just goes right across because the distance it has to travel is so small, achieved by lithography. But in most cases, what the electron is doing is it's going up here, it's bouncing off of that atom, bouncing off of this atom, maybe coming up here, bouncing off that, right? And so it basically does this sort of thing. And it will go backwards sometimes, right? But it's taking a tortuous path forward, okay, from this point to that, right? It's not just ballistically going all the way through. And so because of that, I'm multiplying my electric field by some mobility. And that mobility is modeling how this electron is moving by colliding through. Okay, it's slowing down the whole thing because the electron just is not going as fast as you might expect it to. Right? So this kind of motion where an electron is colliding its way from left to right, in this case, when our electric field is like this, when that electron is doing that, right? So if it's going in this direction here, then this is what we call drift. Okay, so when I say drift current, I mean this. I mean I've got an electron that is slowly making its way. Not slowly, it's still going very fast, but it's bouncing around towards one end, being pushed by an electric field. Okay? And so that's why I define this thing called a mobility for this. Whoops, didn't want to do that. Okay. And so let's keep going with this. And so from here, I guess I have this thing here. So let's go from here to here. Okay, and so I can now write my equation for drift of an electron. So J sub n drift of the electron, that's now going to be Q times n times mu n, which is the mobility of an electron. So a hole will also move through a haphazard way, but its mobility will be different from an electron. Okay, so actually electrons are better than holes. It's easier to move an electron. A hole will generally move slower than the electron because it's tougher for a hole to move, right? For a hole to move, an electron has to go into that hole to create a hole here and so on and so forth there. So in general, the mobilities for holes are smaller, but if we just focus on electrons right here, it's that times electric field. That's a current density, so the units are amperes per square centimeter. Okay, so this is my equation here for the drift current for electrons under an electric field E. Okay? And so now I can do pretty much exactly the same thing for holes. Okay, so for holes, I can write a JP drift equation. That's going to be equal to also Q sub P, which is going to be the charge density of holes, also in coulombs per cubic centimeter. That's going to be times V sub P, which is going to be the velocity of holes, in centimeters per second. Because holes are positively charged, I can write that charge as plus Q times P, where P is the concentration of those holes. Because the holes are moving to the right in my picture on the left, okay, they're going in the plus X direction, so I could say that this is going to be plus mu sub P times E, where mu sub P is the hole mobility, okay, which is about equal to 250 centimeters squared per volt second. Okay, you can see that's about half the mobility that electrons had for reasons that I just described there. And so finally, this whole thing I can write as Q times P times mu P times E, and that then equals to the drift current, or the drift current density of holes. Okay, so I pretty much just derived the same equation for holes there. And so the total current if you have both holes and electrons in sufficient quantities, you have to add these two currents together. So my total drift current, which I'll call J total drift, is going to be equal to the sum of Jn drift and Jp drift, which, if I write that out, is going to be my unit charge Q times N times mu N plus P times mu P times my electric field. Okay, and so this quantity right here is going to be equal to the conductivity. So I can write that as sigma times electric field. And so conductivity, given the symbol sigma, is just equal to this Q times N times mu N times P times mu P. Okay, conductivity is something maybe you've seen before, right? This is also just equal to 1 over rho, where rho is the resistivity. Okay, these are all quantities that people use all the time, conductivity and resistivity. And in semiconductors especially, if we have knowledge of conductivity and resistivity, we can define what's called a sheet resistance. Okay, but before doing that, I guess I'll do that much later on in the course, but let's just define resistance now. A quantity that you've been using at will, right? But now I can actually quantify it in terms of physical parameters. The resistance is just going to be equal to this resistivity rho times the length of whatever thing that I have. And so what thing do I have? I'll draw it, right? So I could draw the same slab. So I have something like this, a rectangular shape in this case. Okay, this is going to have a certain length, L. It's going to have a certain thickness, T, and a certain width, W. Okay, and I'm going to have a terminal here and a terminal there. That's your resistor in your lab, basically. And so its resistance is rho, this 1 over conductivity or resistivity here, which is related to the mobility and the carrier concentration you have, divided by the thickness and the width, which is basically the cross-sectional area of this thing. Right, so that TW is basically this. That's that. Okay, so that is resistance. Okay, and so basically when you talk about resistance, I could say that it's basically a drift current phenomenon. So I'll just say thus resistance in the classic sense that you've been using it all this time is basically a drift current phenomenon. Okay? But that's only one type of current that we get in semiconductors. Okay? There's another type of current, and this other type of current is a little more difficult for people because it's different from what you're used to talking about. Okay? But it's also an equally important type of current, and I would say in semiconductors it might be the more important type of current to understand, and that's diffusion current. So how many of you know about diffusion current? Did you talk about this in any of your classes? Okay, there's a good number of people. Where did you hear diffusion current?
ee105.
130. Okay, the class you're supposed to take after this class. Okay. So some people are, you could take it while taking this class too. Okay, and so diffusion current, what is that? Some of you know what that is, but most do not. Okay, this is now current that flows when there's a gradient in carrier concentration and the carriers attempt to equilibrate. Okay, that's all this is. This is all about reaching equilibrium, and that's it. Okay, everything wants to reach equilibrium because that's the lowest energy state for it. So let me just write this out first. So this is the current that flows when there is a gradient in carrier concentration where carrier, by carrier I mean the charge carrier, either electrons or holes, and the carriers attempt to equilibrate. Okay, so pictorially, what does this look like? This looks like, maybe I'll just give a fish tank example first. Okay, this is just for diffusion. You know what the concept of diffusion is. Right? If I took, say, a fish tank, which is what that is, okay, and I put a barrier between one side of the tank and the other, and all my fish are on this side here. It's obvious what those are because it's drawn so well, but I'll label it fish anyway for you, right? If I remove the barrier, then you know what's going to happen. Right? Those fish are just going to move around, and they're going to be basically at the same concentration throughout the tank, right? They're going to move to equilibrate so that not all of them are on one side. And that happens to everything in life. right? Everything wants to equilibrate. Mountains, given enough time, they'll be gone, right? They'll shrink to just flat land. The earth won't allow that to happen, right? Energy prevents that, right? Energy creates new mountains with volcanoes, all that energy within the earth and that sort, right? But everything wants to equilibrate. So if you allow it to do it, it will. And so let's now go back to talking about semiconductors. So back to carriers. In semiconductors, the way that we will plot this sort of thing is through plots of concentration. And so this is x, so that's distance, right? This is like location in a semiconductor. Okay, and if my y-axis here is my carrier concentration, just through doping or other methods, I can make my carrier concentration different at one location versus another. Okay, so let me say carrier concentration in this case, that's either n of x or p of x, depending on when you're talking about electrons or holes. Right, but say my carrier concentration plot looked like this. Okay, if this were my carrier concentration plot, then the observation here is I've got a low concentration of carriers right here. Right here, obviously, I have a high concentration. Of carriers. And so what's going to happen is the high concentration of carriers want to move towards the low concentration of carriers because it would go to a lower energy state. Right? So these want to go down to there. So that the whole thing would be in equilibrium and go to a lower energy state. So what would happen here is these carriers will move in that direction. Okay, they will just move. And again, they want to move left. To equalize the concentrations. Separate that there. Okay, because that allows them to go to this lower energy state. Right, so this motion in this direction, right, if I have carriers going in that direction, that's a movement of charge. This is diffusion current. And this turns out to be a very important form of current in semiconductors here. So if carriers had their way, oops. Wow. Carriers had their way, then at the end of all of this, that's x again, this is also carrier concentration. This would end up a straight line. Okay? And so obviously this diffusion current, how much current you get, is going to be dependent on the slope of that curve. The steeper that slope, the more the stuff on the right side wants to move to the left. Okay? And so this diffusion current is going to be proportional to this carrier gradient. And in particular, it'll be proportional to the negative of that carrier gradient. Let me just write that. Okay, that's blue. Okay, so if I wanted to write expressions for diffusion current, then for example for hole diffusion, I would write J sub P, now diffusion, so I put diff there instead of drift. Okay, that's going to be equal to the type of charge I have, which is positive charge, okay, times what I'll call a diffusivity, d sub P, times the negative of my concentration gradient. So negative of the derivative of P, which is the whole concentration with respect to X, which means I write this whole thing as minus Q times dP times dP dx, and that's going to have units of amperes per square centimeter. That's for hole diffusion there. And for electron diffusion, a very similar equation. So Jn diff is minus Q times d sub n times minus the derivative of n with respect to x. And so that now ends up being plus Q times d sub n, which is again a diffusivity constant that I'll define in just a second. And that also in amperes per square centimeter. Okay, and so d sub n in this above, that's equal to the electron diffusivity, okay, which is equal to that mobility that we talked about, mu n, times kT over Q. So kT over Q is a very commonly seen quantity. My pen is not working here. Okay, but this ends up being equal to mu n times Vt. So that Vt is that thermal voltage we talked about before. Remember in the diode equation? That's the Vt right there. It's equal to kT over Q. And so let me write out first the diffusivity for holes. So d sub P is the hole diffusivity. That's going to be mu P times kT over Q, or mu P times Vt. And so this whole thing means Vt is going to be equal to kT over Q. K is the familiar Boltzmann constant. That you should have seen in physics. T is temperature. I'm not going to be able to fit that in there, so let me... And at room temperature, this is about 25 millivolts. It is a voltage. Okay, and so I'll say at room temperature, which is about 25 degrees Celsius. Okay, and so just to finish this all up, the total current at location X, which is kind of an interesting thing. The current can change with the location based on what the slope is at that location. I could say J total is going to be equal to J total of the drift plus J total of the diffusion, where J total of the diffusion is just these two added together, right? That's just Jp of diffusion current plus Jn of diffusion current. Okay, so this now becomes your total current equation, including both drift and diffusion components there, both of which will be important when we start talking about semiconductors. But in principle, well, I guess no. So diffusion will be most important for bipolar transistors. Drift will be most important for MOS transistors, for metal oxide semiconductor transistors. And so that's what we're working toward. But before that, we need to understand how a diode works, and that's what we'll do at the start of next lecture. Okay, but we're done today.